Hello everyone, my name is Michael Hammond, and this is a report on Lab 1 in which we discuss constant velocity and how we can draw predictions on the velocity of objects. So getting started, this lab had two main purposes. First was to demonstrate that Newton's second law is an excellent tool to use for predicting future positions, velocities of an object. Second, this lab aimed to introduce us to using computational models to simulate physics situations and to compare this data against what we observe. As for models and physical principles used during this lab, there were many. First, the velocity update formula, v sub x equals v sub I plus f net over m times delta t, provides us with an updated velocity for an object given an initial velocity, the net force of the object, the mass of the object, and a duration. Next, the position update formula, r sub x equals r sub I plus v average delta t, is used to generate an updated position vector for an object given its initial position, an average velocity, and a duration. This particular formula came in handy when we needed to generate data for the system discussed in the lab. However, first we needed to use the velocity update formula to find an average velocity for the object. Third was the position versus time graphs, and these were used to organize and visualize our data generated from the observed motion and the predicted motion. Finally, we had Newton's second law, F net equals dp dt, in which we used to derive the velocity update formula and the position update formula. And it's important to note that when there's no change in momentum in Newton's second law, the net force is equal to zero, meaning we have a constant velocity. As a quick overview of the results of the lab, after concluding the experiment and generating models, we can see that an observed model and a predicted model are extremely similar to one another. It's just that the observed model is not quite a constant velocity. This lab had one important initial condition: an object would be rolling at a constant velocity without changing directions. The system includes only the object, in our case a can, as it is what we were testing on and what the surroundings do or do not have an effect on. While our predicted model had no forces acting on the object, our observed model technically does, and this is the normal force, gravitational force, and friction. As for the process that was followed for this experiment, it went as follows. We recorded an object rolling across a flat surface at close to a constant speed. We used Tracker to track the position of the can at certain time intervals that match the frame rate of our camera. We generated an observed position model from the tracker data. We used GlowScript to create a computational model for the predicted position of the can, and we compared the two models. Code explanation. First, the code initialized some conditions. The mass of the can was set to 1 as it has no bearing on the constant velocity object. An initial position vector was instantiated at 0, 0, 0. An initial velocity vector was set to negative 0.79400. This was calculated by using the first two time steps of the observed motion. Finally, a while loop with the terminating condition that when time is greater than the ending time, then the loop would end, was instantiated. The velocity update formula was used to generate the velocity to be used in the position update formula, and the position update formula was used to get the new position for the object with each iteration of the loop, thus every tenth of a second. The time was updated with each iteration of the while loop to make sure that the position was updated properly. The models, as mentioned before, are extremely similar to one another. The predicted model, however, is perfectly constant. Both models provide data until a time of 0.97 seconds. By the end of the observed model, we can see the observed model reached a position of negative 0.635 meters. Conversely, the predicted model reached a position of negative 0.77 meters. The reason for the difference in the models is because the observed model cannot perfectly replicate a system with zero net force because of the surroundings we previously talked about. The three largest sources for possible error in this experiment are as follows. For one, the observed model is not a true constant velocity, so the model, even in another trial, will inevitably slow down. The amount of force used to push the can could potentially slow the decrease in velocity of the can, but this will not be the same every single time. Next, a tracking error could have occurred, and then a rounding error could have occurred when you put it into a spreadsheet. The question arises, what if the axes were flipped? Well, if the axes were flipped, it's simply the slope would flip. If we're moving in the positive x direction, then our slope is going to be moving in a positive direction. And if we're moving in a negative direction, our slope is going to be moving in a negative direction. So what does this all mean? Well, the experiment proves that computational models can accurately predict observations. And this is especially true when a system has a net force of 0. It also shows that Newton's second law is extremely useful for predicting the velocities and positions of objects. Furthermore, a question is asked on whether or not it is possible to say how many forces acted on the observed model. No, While an estimate can be made, the sheer number of factors that can affect the system is staggering. This Things such as wind are impossible to account for when we have no knowledge of their bearing on the system. Thank you for watching.